Good afternoon.
Okay, welcome back, everybody. All right, ready for another week of exciting chemistry, right? All right, a couple of things. Oh, hold on, I'm gonna let a few more people in. Okay, well, any questions, comments? If not, we will jump into the next chapter, which is chapter 5. Now, up to this point, we started to build the model for the atom, and we talked about how we are able to determine what the particles, subatomic particles, were made of. We talked about the proton, the neutron, and the electron. The basic model was in the nucleus was the proton and the neutron, and in some place somewhere in the atom is the electrons. Okay, so that's our basic model. Now we're going to focus on the electrons, because it turns out that based on our model and based on experimental data, that these electrons exist in very specific energy levels. Now, I direct you to our periodic table. Now, for the one that you have, if you don't have it marked up, you may want to mark it up with the following information. If you look in the far left column, you'll see that I have marked the rows going across the periodic table, starting with hydrogen, goes from hydrogen all the way across to helium. That's row number 1. And then from lithium all the way across neon, row number 2, and etc. So there are 7 rows. Okay. We're going, not rows or across, going across horizontal. They have specific names, and we'll talk about that at a later date. But these represent specific energy levels. Keep that in mind, okay? And I'll be referring to the periodic table quite often. All right, now, what we established was that we put in an AMU, an atomic mass unit, a relative mass unit for the proton and the neutron. For the electron, because they're so tiny, we gave them essentially a atomic mass unit of 0, saying it's essentially 0 mass. They do have mass, but the mass is so tiny that they behave like light. So what we're going to do is going to talk a little bit about light and how light travels through space and so forth, our model for light. And keeping in mind that we're going to be using the model of the light to represent the model of the electron and how it behaves with respect to energy. It's all about energy, bottom line. It's all about energy, okay? So light, as we know, exists based on our model as waves. And electrons, as I've stated, being so small, also have wave properties. So how do we describe a wave? Well, we have this curve here, okay, that represents a propagation of light traveling from point A to point B. Now, we can take a couple points, take a point from, let's say, here on top of this hill, which your book calls the crest, or the bottom of the hill, which is the trough, whatever you want to call it. But if we take a point from top of the hill and then take another point on the bottom, on top of the next hill, that distance is the measured quantity. That distance is what we call the wavelength, okay? That is the length of light, which also is going to be the wavelength of this electron as it behaves as light, okay? Now, there's a symbol here that's called lambda, the Greek symbol lambda, that represents the wavelength. And that is the distance between, in this case, from the peak. Now, you can pick any place on a wavelength. I could pick the bottom here, right here. But if I pick the bottom of the next wavelength, that distance is the same distance as the top. Okay, that is the wavelength of this particular model of whatever light we got here. Now, the frequency, which we represent by this letter, looks like a V or mu, the Greek symbol mu. We got lambda for the wavelength, and then frequency listed as the letter V. And that is the number of wavelengths that occur per given time, which the standard, the reference point is 1 second. And so basically saying, well, how many things happen? How many wavelengths happen within 1 second? You may be familiar with this with your own computer. You have a computer with a processor operating at, say, 2 gigahertz. What that is telling you that in 1 second, there are 2 billion things occurring in your computer within that time of 1 second. Obviously, the higher the speed, the frequency, the faster you can do things on your computer. The higher the speed, things go a little quicker. Now we're in the gigahertz, for example, and I use that example because to give you a reference point, so it wasn't too long ago, you know, say 30 years ago, that we were in the megahertz. I mean, very tiny, you know, very, very tiny as far as speeds of computers, but that was the frequency. So how many things occur, and I'll give you a general definition, how many things occur within 1 time second, all right? Okay. Now, if we look at this model here, or these wave diagrams with 2 different wavelengths, you can see that the top one, when we do a relative measurement, if we look at the distance between hills on the top and the bottom, you can see graphically that the top one has a longer wavelength than, say, the bottom one. Okay, has a shorter wavelength. Okay, so that's one thing you can take away. Now, what is associated with light that has long wavelength is that they have light, electromagnetic radiation has associated with it energy. Okay, sometimes it is very weak energy, sometimes it's very strong energy. If you don't believe me that light has energy, you may be familiar with laser beams that can cut metal. That's a lot of energy, pretty powerful, and that's just light. Okay, I call it electromagnetic radiation. We use the term electromagnetic radiation because that encompasses all kinds of wavelengths, not just laser beam light. Okay, and I'll have more on that in a second. So anyway, associated with a long wavelength, we have a low energy and a low frequency. A good example of this would be like radio waves. Radio waves, you know, you get on your car, turn on the radio, you are listening to, you know, radio waves in the meter length. They're very big wavelengths, and very weak with respect to energy. You normally don't cause much of a problem physically when you're hit with radio waves. However, when you have very short wavelength, let's say associated with short wavelength, let's say X-rays, they have high energy. Okay, their wavelength is small, but their energy is high, and their relative frequency is also high. Okay, now you might think, well, what do you mean by the relative frequency? Well, let me color this a little bit different. Let's say, for example, that this distance from here to here was 1 second. Okay, and we're clocking these things. Well, you can see that in 1 second time, we probably have maybe a wavelength and a half pass through that 1 second, compared to the bottom one, where you got maybe three wavelengths going within a 1 second. So you can see that it has a high frequency. So maybe you got 4 wavelengths per second for the bottom example, and the top one, maybe you got 1 wavelength per second. So it's a low frequency. Okay, so the takeaway from this is the following. One, with respect to electromagnetic radiation, that when we compare 2 different wavelengths, the long wavelength has low energy and low frequency, whereas the short wavelength has high energy and high frequency associated with it. Okay. With that in mind, you can look at a diagram and be able to answer the questions just by inspection here, just by looking at it. You can see that one, the wavelength of A compared to B is much bigger. The distance between the two hills, okay? So that's associated with it. A long wavelength on top means a low energy compared to B. So B would have the higher energy because it has a shorter wavelength. And A would have the lower frequency because it has the longer wavelength. Okay. So just by looking at the diagram, you can be able to distinguish differences like that, energy, frequency, and even wavelength, just by looking at the diagram. Now here's the electromagnetic spectrum. Okay. We have on the right side wavelengths that are pretty big, like the radio. Okay, it could be in meters length. Very big, very little, energy-wise, not so much of a problem associated with radio wavelengths. Whereas on the other end of the spectrum, you have gamma rays, which you find out in space. They're extremely small wavelength, extremely high energy, okay? And in between, you have, starting from the radio, what's a little bit higher in energy is microwaves. You're familiar with microwaves, and next time you pop your popcorn, you're using a microwave machine, okay? Their energy is a little bit greater than a radio wave. And then above that, you have infrared. That's a little bit with respect to energy-wise. A little bit higher energy are the infrareds. And then what we see is called the vision. Now, this spectrum is not the scale, because what we see really is extremely small amounts. Because we're invisible, our eyes have two types of cells in our eyes. We have cones and rods. Cones are pick up on color light, and the rods pick up on black and white grayscale. Okay. At night, the rods take over, because you notice at night you're basically looking grayscale until a light hits whatever you're looking at, and then it brightens it up to color. But we have a small spectrum that we can see. Then above the visible, we have ultraviolet. We know how bad they can get. Being living out here in the sun in Arizona, UV light can be very devastating to your skin, but more so, it can also be devastating to plant life and so forth. That UV light that's coming from the sun has really increased, because what used to be up in the atmosphere was a layer of ozone, not the same ozone that's down here on the ground, but way up in our atmosphere. And that ozone used to protect us from high UV radiation. Well, we got a big old hole in that ozone layer, and there's more UV light coming into the earth. You might notice that if you ask your parents and grandparents as far as the number on your sun block, that number has increased over the years. Okay. Then above the UV, we got the X-rays. So be familiar with the range here, and where they're at, and how we got low energy over here and high energy on the part of it. Okay. All right. So that is our model for the electromagnetic spectrum. Now, the last chapter we were talking about J.J. Thomson and Rutherford, and some other scientists. I mentioned there are a number of other scientists that were here during this time period. So here we are, 1900 again, like in the J.J. Thomson era. Scientist by name Max Planck, a very famous scientist, he proposed a controversial idea for the time. He believed that energy was emitted in small bundles, which he called quanta. And so energy wasn't a continuous phenomenon, but there was spurts, or I should say, the energy was in packets of specific amount of energy. Okay. Max Planck, famous scientist, there was a Max Planck Institute in Europe named after him. So energy is not continuously emitted, okay? he put the term photon, used the term photon to name a energy packet of light. So sci-fi people pick that up. Now you got photon torpedoes. So talking about light. So what the bottom line is this, he called them quantized. The energy levels are quantized, okay, with respect to light. Now, so before I go further, if we look at a wedge at the left, that will represent continuous energy, okay? If we look at the stair step, this is what Planck was proposing. Now, down at the bottom step, down here, is what we call the ground state. Ground, the bottom state. All energy, all molecules have a ground state, okay? And what happens is when matter absorbs energy or even gives off energy, it gives it off with a specific amount of energy that could be represented by the first step. That first step is a specific height. So that is a specific amount of energy associated. And as we go through the steps, it's not continuous like over here, but it's steps. And the higher the step, the higher the energy, the more energy involved, okay? So it's quantized energy. And that's how we were treating light. So what Niels Bohr, again, here's another scientist, turns 1900s, okay, just as famous as the other guys. He proposed that electrons of the atoms orbit around the nucleus. And he went further to say that these electrons that are orbiting around the nucleus are in distinct energy levels, okay? Hence back to the periodic table, energy levels 1, 2, 3, 4, 5, 6, 7. Okay. So the electrons are now quantized, which is what Niels Bohr proposed. Okay. So the electrons orbit around the nucleus kind of in three-dimensional, sort of like our solar system, but our solar system is more two-dimensional. The electrons are more three-dimensional, and they're all over a specific area. Okay. And they orbit these energy levels. You may see the term shells. I prefer to use the term energy levels. And the periodic table, as I showed you, has 7 distinct shells. If you look at the periodic table, bring it up here again. The first energy level, change the color here, encompasses, number 1, hydrogen. Oh, try that again. Hydrogen, there's something going on here. Hydrogen to helium, that's number 1 energy level. Second energy level from lithium all the way across to neon, okay? And third energy level starts with sodium all the way across with argon. In the fourth one, I'll stop there, it goes from potassium all the way across to krypton. Okay, so those electrons for those atoms in that period, that is the outermost shell. Remember that, as I stated, there's 7 energy levels. Now, when you start off with energy with hydrogen, there's only 1 electron, 1 proton, 1 electron. It's going to occupy the very first energy level. Okay. And then when you go across to helium, we're going to notice that it's going to also occupy its 2 electrons in the first energy level. When you go to lithium, number 3, now it has 2 energy levels. It has the first one where lithium has 3 electrons. 2 of those are in the first energy level. And then the 1 electron, it's all by itself in the second energy level. Okay. And that's how you proceed. You build up. And when you get done with neon, which is number 10, okay, number 10 has 2, neon has 2 energy levels. Energy level number 1 has 2 electrons, and then those 8 electrons that neon has of the 10 are in the second energy level. When you wrap around to sodium, guess what? Now sodium, it's 11 electrons. The 1 is on the outside. So you start building up, going around the periodic table. I will be referencing the periodic table quite often when we talk about these electrons and how we build them up with respect to their energy levels, because we're going to learn that within the energy levels, we're going to have sub-levels that we call orbits. Okay, so every orbit has a specific radius and a specific energy and a certain distance. You know, radius has a certain distance from the nucleus. And so we have shown here kind of two-dimensionally. You have the nucleus here on the right side image. And then the dotted lines represent energy levels. Energy level number 1, number 2, and number 3. Keep it in mind, 3-dimensional. In fact, if you look back at my screen, the back screen, those are representations of the different energy levels that we're going to talk about. I'm going to have a slide on these screens, but the very first one is round in shape. And then the next one, you can see there's 3 yellow ones, have an interesting shape. And then the blue ones, there's 5 blue ones. And then behind me, there's 7 green ones, okay? These are the orbits that are within the energy levels, and within the orbits, that's where the electrons exist. Now, how did this come about? This came about because what we call line spectrum, a line spectrum. Now, what happened was this: basically, an element was placed in a, think of a good classic example is a neon tube. A neon tube is nothing more but a glass tube, vacuum tube, filled with an element, okay? And then it has electrical outlets that you plug in electricity. When you run electricity to that tube, the fluorescent tube, for example, it excites the molecules, and the molecules being excited get pushed from the ground state I just mentioned to the excited state. Well, they're not going to hang out there very long. They come back down to the energy that they started from, okay? Because that's nature being nature. It cannot hang out there in the excited state very long. It comes back down. But in doing so, it releases the energy it absorbed, because of conservation of energy. That energy is released in the form of heat or light. And hence, that's why the fluorescent lights you're able, or a neon light, you see the light. The molecule inside getting excited, and it's emitting light from coming back down to the ground state. And if you touch it, it also gets a little warm, okay? So there's light and a little bit of heat. That occurs, that light is emitted. If we run into a special process, we get what's called an emission line spectrum. The same thing happens next time you see a rainbow, okay? When you're looking at a rainbow, you see the visible wavelength, because what's happening, the water droplets are taking the light that you have, that you see out there, and breaking it up into the different wavelengths. And because we're sensitive to that wavelength, we see the rainbow, okay? So what was done is the tube on the far left is filled with hydrogen. Okay, right in here. We put a electrical charge through it, okay, power it up. This tube lights up because the hydrogen gas gets excited, then releases the energy that it got excited from as light. So that light then is run through these slits, and then nothing fancy. All they did is just focus the light that it emits. Then the light is focused onto a prism. Well, if you're not familiar with the prism, that operates just like the water droplets out there on your rainbow. It takes the light going in and breaks it up into the different wavelengths, okay? And then on the wavelengths, you can see we got the 4 different colors. This is the emission. This is specific for hydrogen. It has a violet color, blue violet, and green. and a red line. And that distance, and now we can do calculations, but every line there is a wavelength. NM is nanometers, 10 to the -9. Okay, so we got 410 nanometers, 434. So here's the wavelength of light that hydrogen has emitted. Okay, very specific wavelengths that we can associate with that specific amount of energy. All right. Now, this is the fingerprint for hydrogen. That's how we can look at the lights from outer space, and we can analyze the light. And the light is the emission spectrum. It's a little more complicated than I just stated, but we can analyze the emission and determine what's out there. Okay, so then, not only hydrogen, but you can do this to multiple different elements. And here you can see in the far left, you got lithium, sodium, potassium, rubidium, cesium, so on. Metals like mercury and neon. And each one has a specific emission line spectrum. It is unique to that particular element. Okay, or compounds also have their own spectrum. And so that tells us that what is happening here is that these electrons are being excited from the ground state to the excited state, to the next energy level. Okay, and that's demonstrated here. So let's say we have our electron here orbiting around the nucleus. Okay, and so it gains energy by electricity. Okay, it causes the electron to get excited and move to the next energy level. Now, this is very key principle in that it just doesn't arbitrarily go to the next energy level. It goes to a specific energy level. So it went to a next energy level, or a specific energy level. This is the excited state. And this would be in the ground state. Okay. Ground state. Well, it cannot hang out there in the excited state very long. Nature being nature, the electron will go back to the ground state. And in doing so, based on the conservation of energy, it must release the same amount of energy it gained to get up to the excited state. And this represents something going out, either being light or heat. Okay. If you have the old-fashioned incandescent light bulbs, a little filament, electricity runs through that filament, excites the molecules in the wire. They get hot. The old the old light bulbs get very hot. The screen that you're watching right now, those molecules on the screen are getting excited and then dropping back down the ground state, emitting that light that you are picking up as an image. Okay. All right. So each element has its own energy levels and very unique. Now, there are 7 energy levels as per our periodic table. Now, within the energy level, it's been shown mathematically. This is the realm of what we call quantum mechanics. I don't know if you've ever heard of that term before, but quantum mechanics is a lot of it's mathematical based, a lot of heavy duty, high caliber math. And what quantum mechanics tells us is that within the energy levels, there are sub-levels that we're going to also call them orbits or orbitals. Okay, there are 4 of them, designated by the letter lowercase s orbital, p orbital, d orbital, and f orbital. Okay. All right, so in the first energy level, which I showed you in the periodic table, encompasses hydrogen and helium only. There's only one s orbit. One orbit, that's it. And that's the S. And we demonstrate that, we show that by putting the letter 1, which represents the first energy level, and S, which represents the energy level, the orbit for that first energy level. Okay. For the second energy level, which is from lithium all the way across to neon, those outermost electrons, all those electrons occupy, not only do they occupy the first energy level, but now they also occupy the second energy level, of which there are 2 orbits, the S and the P. Okay, notice that all of the 7 levels will have the S. So you got the 1S, the 2S, the 3S, the 4S, all the way to 7S. The only difference between the 1S and the 2S, they look the same, but they're just bigger. You know, think of it this way, as the 1S being a golf ball size diameter, okay? Maybe the 2S being a baseball size diameter. The 3S may be a softball. The 4S may be the size of a soccer, and so on down the road till you get the big old giant beach ball at the 7, okay? They all look the same, but just different energy levels. At the second energy level, we introduce the P, okay? The P orbit. The third energy level, we introduce the other orbit, which is now the D. Now, like I stated, everybody has the S. Okay, change the color here. Everybody has the S orbit. There's a 1S, 2S, and 3S. Starting with the 2, we introduce the P. So down the road from 2 to 7, they all have the P. So you have the 3P. It is at the third energy level that we bring in the D orbit. Okay. In the fourth, we introduce the final orbit, which is the F. Notice that we still continue with the S and the P, and the D continues, and then the F is where, at the fourth energy level, where we start looking for the F orbits. And if we went down the road, 5S, 6S, 7S, and so down, and 5P, 6P, 7P, etc. Okay, etc. So, so there are 3 orbits, 3 or 4 orbitals, S, P, D, and F. Okay, and 7 energy levels. Now, further information. We then find out from the mathematics that there's only 1 S orbit, regardless of what energy level it is. 1 S orbit. No, first of all, every orbital can handle a maximum of 2 electrons. So every S can handle 2 electrons. Every P can handle 2 electrons. Every D can handle 2 electrons. And every F can handle 2 electrons. What is additional information is that there's only 1 S type of orbit. Okay, there's only 1 S type. There are 3 P orbits. Okay, there are 5 D orbitals, and guess what? There are 7 F orbitals. Okay, each one can handle 2 electrons. So the maximum number of electrons in each orbit is 2 for the S, 6 for the P, because there's 3 of them, there's 2 in each orbit, 10 for the D, and guess what? 14 for the F. Okay. So keep that in mind. Let me re-emphasize this again. 7 energy levels. Okay. With respect to the orbits, there's only 1 S orbit, and they only begin in the first energy level. Okay. And there's 3 P orbits that begin starting with the second energy level. And there are 5 D, which begin starting with the third energy level. And there are 7 F orbitals starting with the fourth energy level. Okay. Clear as up. Clear as mud, right? Now, it'll become clear here in a bit. So that's again, two-dimensional diagram. With the different energy levels and which orbit or different energy levels and which orbits orbitals come in and what energy level. So the energy level 1, there's only S, that's it. Energy level 2, we got the S and the P. 3 is we got the S, P, and the D. And 4, we got the S, P, D, and the F. Now, what these orbitals are mathematical equations. Okay, that's all they are, mathematical equations. And when you take any mathematical equation and you plot data, generate data, it will give you a plot. And when you do that three-dimensionally, you end up with an image of what that orbital may look like. Okay. Now keep in mind that every orbiter can handle maximum 2 electrons. So we're going to show you some pictures here in a bit. So let's go back and reemphasize. There's one S orbital. Each one can handle 2 electrons. So for every S orbital, regardless of what period it's in, what energy level it's in, it can only handle 2 electrons, maximum. The P's, which again began in the second energy level, have 3 P orbitals. Notice, look at the image behind me. That's the yellow. There's 3 P's, okay, in the 3-dimension, X, Y, and Z dimension. And each one can handle 2 electrons. So there's a maximum of 6 electrons for all of the P orbitals, okay? The D is the blue ones behind me. There's 5 of them, kind of a weird looking shape, okay? But that's okay. That's what the mathematics gives. Now, in each blue can handle 2 electrons, so you have a maximum of 10 electrons. And then the green, of which there's 5, okay, each one can handle 2, gives you a maximum of 14 electrons for the F orbit. All right, so if you have your periodic table, you can follow along because I'm going to equate this box system here with the periodic table. All right. So in reality, if you could, I'm gonna have to make a new diagram, but I really should flip this over starting at the bottom, because when you feel electrons, you start with the first energy level. And so really this will actually look like an upside down pyramid. Okay. Now every box represents an orbit. Notice energy level 1, we have 1 box that represents labeled S. That represents the S orbit. And as stated before, in the second energy level or the second period, we also have an S, but we introduced the P. And there are 3 boxes because there are 3 P orbitals. Okay. Notice energy level, 1 box for the S, 3 boxes for the P, and 5 boxes for the D. That's where the D's come into play when we reach the 3rd energy level. And then the 4th energy level also has the S box, 3 P box, 5 D box, and now we have 7 F boxes. Okay. Now every box represents an orbit, and every box can handle 2 electrons. Now I'm going to designate my electrons as arrows, and I'm going to put them as opposite directions, because one of the rules is that when there's 2 electrons in an orbit and they are orbiting, they don't orbit in the same direction, they actually orbit in the opposite direction. Okay, so it's actually been shown that if you can change the spin of one electron, the other electron automatically will spin accordingly. Anyway, if we look at hydrogen, hydrogen's element number 1, right? It's only got 1 electron, 1 proton. And so its electron occupies the very first energy level and the very first orbit. And let me change the color here and make it red. And I'm going to represent that by the arrow. Okay, to make a difference which direction it is. But that's hydrogen. 1 electron, right? Now go across the periodic table. And you got helium. Helium is element number 2. It's got 2 electrons. So its electron also is occupied in the first energy level and in the s orbit. So now that is full. Okay. So that energy level is full, and that will be representative of helium. Now, if you look at lithium, go around the periodic table, you start in the far left, you find lithium, which is number 3. Lithium has 3 electrons. 2 of those electrons will occupy the first energy level, and that's designated by what I just did. And then the last one will be in the s orbit. Now, the s orbit gets filled first before the p. Within the energy levels of these orbits, s, p, d, and f, the energy level of the s is lower than the p, which is lower than the d, which is lower than the f. And so the order of filling up the orbits is s first, then p, then d, and then f. Okay. Also, if you have more than one orbit within, like the P, you got 3, you fill each one individually first before you double up. Okay. Now we'll use an example in a second. Now, who can tell me what group we're at lithium right now? This represents lithium with its 3 electrons. What group is lithium in? Who can tell me that? What group number? It's a Roman numeral number. It's on top of that group of where lithium's at. What is it? What Roman numeral number is that? Anybody can see that? You have your 1A, exactly, Samantha. That 1A, if you recall, I may have mentioned, it represents just for the A elements. It doesn't work for the B ones. For the ones that labeled Roman numeral A, represents the number of valence electrons. Those are the electrons in the outermost shell, right? Level 2 is the valence shell for lithium. And lithium has only one of those 3. One of them is the outermost shell. So you can see where that outermost shell electron, where it occupies. It is in level 2. Okay. Now, what element is next to lithium? What's next? What's after lithium? Beryllium, right? And they have how many? 4 electrons, right? And guess where that 4th electron occupies? Same spot. Now, as Be. Now look, what group is beryllium in? What Roman numeral group is it in? 2A, exactly. 2A, which would tell you that there's 2 valence. There's 4 electrons for beryllium. Of those 4, 2 of them are in the outermost shell, which is level energy number 2. Okay. And that has 2 valence electrons. Those 4, the innermost, are inside, they're full now. Okay, so there's 4. Now go across the periodic table and guess who you see? Boron, right? Boron, going off memory here. I don't have it in front of me. So how many electrons does boron have? Five, exactly. And guess where its electron, that 1 electron goes? Because if, excuse me, this is boron, it has 5 electrons. The first 2 are full. The next 2 fill up the S, because like I stated, the S gets filled first. So we fill on the, we can put a maximum of 2 in the S, and there's 1 left. So the only place it can go is in the P. Okay. And so now, if you look at the group number for boron, it's in group Roman numeral 3. Okay, which tells you that 3A. There are 3 valence electrons of the outermost shell. So of the 5 electrons boron has, 3 of them on the outside, outermost shell, and the other 2 on the inside. Now you can continue all across the periodic table, and as you do that, you fill in the electrons, and like I said, you got to fill in each orbit first before you double up. And I continue to go all the way around, and I can fill up the rest of the P. Okay, now with that, the way I wrote this, who can tell me what element would this represent? All my electron level, all my energy levels are full. I got a total of 8. Got 2 in the S, 6 in the P. Then at the second energy level, and then my 1s is full. So who does this? Who would this represent? Who has 10 electrons? Exactly, neon. Neon has 10 electrons, it's number 10, right? Of those 10 electrons, guess what group is neon in? It should be group 8A, Roman numeral 8A, okay? That tells you there's 8 valence electrons, and guess what? Look at here. You got 8 on the outermost shell, level number 2. Of those 8, 6 of them are in the P orbit, 2 of them are in the S orbit of the second energy level, and then the other 2 are in the first energy level in this S orbit. Neon has satisfied that magical 8 number that we're going to be looking for all the time. Now the outermost shell is full, and the book uses the term happy. I guess the molecule is happy because it's got 8 electrons around the outermost shell. And from the energy perspective, it'd be difficult to add one more electron. Why? Because the only place I could add another electron, I have to take it up to the next energy level. And so from an energy perspective, that's not the best thing to do. Second of all, I have a hard time, it would have a hard time removing any electrons. It would take a lot, it can do it, it would take a lot of energy to get rid of remove any of the 8 electrons in the outermost shell, because they're being held on tightly by the 10 protons that are in the nucleus. And so it is in the stable format, if you will. It's a noble gas because it won't readily give up its electron, and I shouldn't say can't, nothing's ever can. Its energy perspective to pick up an electron just doesn't make sense. Now, after this is neon. Who is number 11? Okay, you have to go to your periodic table, go around the horn, and exactly it's sodium. And guess where sodium has 11 electrons, right? So I have to put that electron for sodium in the 3rd energy level. And if you look at where sodium is, it's in the 3rd period. Okay, and look at what group it's in. It's in group, we're back to group 1A. Okay, which tells you again, like if hydrogen was in the beginning, I have 1 valence electron. Now, but something to think about, because we're going to talk about this a lot, is metals want to lose electrons. And I don't know if you recall, but I said the driving force is to obtain that happy 8 number. Okay, and guess what? If this sodium metal loses this little electron all by itself, the next layer in is full, and it has that magical 8, and it's happy. Okay, so sodium has the tendency to want to get rid of that 1 electron sitting here, then more so than trying to pick up energy, more electrons to put on these orbits, because it wouldn't be stable. Because to stabilize things, you got to have enough protons, and if you want to get more than here, you got to add how many electrons to fill this up. Oh, let me ask you this: for the first energy level, what is the maximum number of electrons that you can put for the first energy level? 2, exactly. Okay, for the second energy level, what is the maximum number of electrons you can put in the second energy level? 8, you got it. And finally, not finally, but the third energy level, what is the maximum number of electrons you can put there? 10. You sure? Yep. Okay, try again. Look at count the boxes in third energy level and then multiply that by 2. See, we got 1 S, we got 3 P's and 5 D's. So the maximum of D's I can put, remember, each box can handle 2, I can put 10 there. For the P, I can put 6, okay? Exactly in 2. So total is 18. You got it, all right? That's the maximum number of electrons. So occasionally, be careful with the question asked. They may say, well, what is the maximum number of electrons for the third energy level? Okay, well, 18. Okay, fine, because I got 5 Ds, 3 Ps, and 2 Ds, all right? Which would be different than asking you, what is the maximum number of electrons that I can put in the D orbits? But that would be 10. Okay, that's it, 10. And then I'll let you do the math for level number 4, but double check my math, 32. Okay. On there, you can put in 14 for the F, right? And 5 for 10 for the D, 6 for the P, and 2 for the S. All right. So that gives you an idea of, you can see here the beginnings of why some elements want to lose electrons and some elements want to gain. Now, if we backed it up and went to the second energy level, and we took out one of these electrons from one of these boxes here, you will have an halogen. Okay, you will see. I won't confuse it, and we'll go from there. We'll talk about that later. But the driving force is either when a nonmetal wants to gain electrons, it's because the p orbit is empty, and it wants to pick up electrons to fill in the p orbits. If it's a metal, it wants to give up electrons to get rid of those outermost electrons that are out there all by itself. And it's just easier just to give them up than to try to hold on to them. Okay. All right. So you're at sodium and you continue as you go across. Now, the confusing part is this. Not that it's not confusing yet, but when we get to the d orbits, the scenario is this, that these d electrons don't come into play until you reach the elements in level 4. Okay. Because it turns mathematically that these d orbits are at a lower energy level than the energy level that the element is actually in. And so notice we're in period level 3, but when we get to the D, this is 3D here, orbitals, those come into play for those elements that are in the 4th energy level. I'll give some examples later on. And then even to make it a little more confusing is when we get to the F orbits, these F electrons come from those elements from the 6th energy level, because those orbits, the F orbits, tend to be 2 energy levels lower in energy than from where they begin, where they get them from that particular element. Whereas the D's, it's only 1 energy level in. Okay. We won't do a lot with the D's and a lot with the S. We're going to do a lot with the B, the S, and the P's, and probably not just stop or not go as far as the 3rd level. Okay, so. All right. So you notice hopefully that we went sequentially. We went throughout the elements and demonstrated where the electrons are being filled up and the energy level that they're in and what orbit they're in. Okay. So when, as I mentioned earlier, these orbits are mathematical equations. Okay. And when you plot the data, you get an image that looks like this. So it's circular in shape. And what that does is shows a probability. If we were to do a cross section of it. If it was a cross section, in the middle would be kind of lighter, much lighter in color than the outermost, because the likelihood of an electron being in the nucleus is very low. So we're talking about the probability of an electron being somewhere in that given space. Okay. Some concern about this particular model. Unfortunately, right now it fits the experimental data. Is it the right model? We don't know. You know, there are some scientists, specifically Einstein, wasn't too crazy about it, because if you think about it, we just talked about energy being in specific energy levels, right? Very specific. And now we talk about the probability of an electron being in some place. So on one hand, we're specific, and the other hand, we're saying, well, maybe there's an electron here, maybe it's not. It's, you know, but unfortunately, that's the best model we got at this point. And so that's what we study until we learn otherwise, or our model gets improved, and it has improved over the years, you know, since the 1900s. The p orbits are three-dimensional. Given here, there's three of them, and they're along the lines of the x, y, and the z axis. So each of these orbits, we call them dumbbells because of the shape. The s orbits are round in shape, like a ball, and the dumbbells for the p's, and there's in the three axes, and each one can handle 2 electrons. Okay. So, but when we get into the D's, denoted by the blue color here, they get some wild looking colors. And this again is based on the mathematics of the quantum mechanics. And you can see they get pretty wild looking. Okay. All right. Now, how we demonstrate the electrons for an element, we use what's called the electron configuration. You already saw the beginnings of it, where you have the numbers 1s, 2s, 3s. That 1 represents the energy level. The coefficient is the energy level. And then the letter afterwards represents the orbit, be it S, P, D, or F. Now the sequence, if you recall that picture, the upside down, where it should be an upside down pyramid, you fill up the electrons with the first energy level, and then the second, the third, and so forth. So the sequence is as follows: 1s, 2s, 2p, 3s, 3p, 4s. Okay. And this diagram here kind of helps you follow the sequence. You fill up the 1s first, then the 2s, and 3s, and then finally the 2p, and then the 3s, and so forth. Okay. Now you can use that, and that's perfectly fine. I tend to emphasize using the periodic table because all the information you need is right there in the periodic table. Okay. And based on the position of that element, you can very quickly write out the electron configuration for whatever element is given. Okay. So, for example, if we use that sequence that we just talked about, and we look at carbon. Now, earlier I said the number is the energy level, the letter is the orbit, and then the superscript represents the number of electrons. So 1s superscript 2 tells you it is the first energy level, 2 electrons in the s orbit. Okay. Then the next energy level is 2s2, superscript 2. Okay. And once the S is full, you move over across the periodic table, and you start filling in the P's. So the electron configuration for carbon would be 1s2, 2s2, 2p2. Now notice if you go back and look at the periodic table, that carbon is in group 4a, which tells you there are 4 valence electrons, okay? And so those 4 electrons are on the second energy level. 2 of them are in the S, 2 of them are in the p orbit, okay? Now, and that is by following the sequence given in this diagram. Okay. And this is a refresher about the different orbits, so 1s, 2s, and 2p, and so forth. Now, what I'm going to do now is show you how you can use its position on the periodic table. So you have 2 choices. Just memorize that sequence and follow that, or just look at the periodic table. Now, if you look at the group 1A and 2A, the far left, okay, think of those as the S elements, and they're written here in blue. So the first column is 1s1. Second column is, or I shouldn't say 1s. If you're dealing with 1s1, it'll be s1, second column s2. Remember that the s orbits can occupy 2 electrons only, okay? So those electrons are, as you go from the left to the right, you start filling the S. So this will be S1. And then when you go into beryllium, it'll be S2. Now, if you shoot across the periodic table, notice something. You have, in the yellow column, there are 6 columns. 1, 2, 3, 4, 5, 6. Remember the p orbits? There's three p orbits. Each one can handle 2. There's a total of 6. So you got p1, p2, p3, p4, p5, and p6. Okay. Now think of these guys, the B elements. They have their own name, but think of them as the D elements. And remember how many orbits in the D? There's 5, right? Total of 10 electrons. Guess what? D1 all the way across to D10. D1 to D10. Okay. Now think of these elements. They all have their special name, the lanthanide and actinide, but they're the ones that come out of the periodic table. Those are the F. And the F had how many total electrons? There's 7 F orbits. Each one can handle 14. And so you can go from F1 all the way across to guess what? F14. Okay. So the periodic table corresponds with how the electron configuration is set up. So we can quickly remember the first 2 columns. We think of those as the S elements. Okay. The inner elements in here, think of those as the D, so D1, so forth. And then the F, the F1 to F14, and then the P's in yellow become P1 to P4. I didn't put the coefficient because it depends on what energy level they're in. So 1, 2, 3, 4, 5, 6, and 7. Okay. And so with that in mind, I'm going to do some quick examples of that using the periodic table. All right, so let's clear this up. All right, so let's go back to carbon. Okay, well, I want to maintain this. That's what I mean. Take your periodic table and mark it. Okay, now let's do carbon. Okay. Well, we know carbon is in the second energy level, okay? So that means that the 1s and the 2s are full. Because carbon has how many electrons? How many electrons total does carbon have? Didn't have 6? Exactly. We have a total of 6 electrons to work with. Okay, now it is in, by marking where carbon's at, I know now that it is in the second energy level, which means that the first energy level is full. So of those 6, 2 of them are already filled up to 1s. We're going across the periodic table, so that means we got the 2s full, and then we got the 2p I can write, okay? Because I know carbon's in the second energy level. I know there's s orbits and p orbits. Well, we fill the s first. Okay, so I put a 2 there. And so of this, I got 4 electrons already accounted for. So there's only at least 2. And guess what? Remember, I went across here. P1, P2, P3, P4, P5, and P6. Well, carbon's in the P2 column, and I just stick a 2 there because it's in the second energy level. See how quick that was? So that is the electron configuration for carbon. And guess what? What if I did nitrogen? Well, just one more electron. I put a 3 there, and I'm done. Okay. Now let's say I want to do neon. Well, I know there's 10 electrons there, and I'm still going across. So that P becomes, that P is P6. So now I filled it already. 1s2, 2s2, 2p6. Okay. That's the electron configuration for neon. And if I went down to sodium, that's 11. It's in the third energy level. I can very quickly go 3s. Okay, because I know it's in the third energy level. It's in the first S column, and that's S1. Okay, and I do magnesium, that becomes S2. So you see by its position on the periodic table, we can very quickly, let's do a couple more real quick. Let's do oxygen. All right. Now, I don't even have to know how many electrons it has. Okay, because I know what I know is I marked up, I'm in second energy level. Okay, so that means that the 1s2 is full. That's full of electrons. Then I know that the 2s2 is filled up. So that's filled up. The 2s2 is filled up because I'm going across the periodic table. Then I count the column because now I know I'm in the P columns here, the P elements, and I know 1, 2, 3, 4. It's in the fourth column of the P's. So that's the electron configuration of oxygen. You see that? Huh? Let's do one that's a little bit longer. Clear that up. Let's do phosphorus. Okay. All right, so I got phosphorus. Again, I got 1, 2, and 3. What I know about phosphorus, it's in the third energy level. So that tells me that the first energy level is full. So that's 1s2. The second energy level is full. That means the 2s2 and the 2p6, right? Now I hit the third energy level. So that's full. So 3s2. And now I hit the same energy level with P because I'm in the P element. So I go 1, 2, 3. This is P superscript 3. And that is the electron configuration for phosphorus. Okay. And if I wanted to do sulfur, I just changed that 3 to 4, and now I got sulfur. And if I wanted to do argon, I changed that S to argon, and now I changed that 4 to 6. Now I got argon. So see how that works with respect to using their periodic table. Right. Now, we don't have to worry about the d orbits until we hit the d elements. So if we were doing this guy right here, then we would be, remember, this is where the d's come in, and we would expect 4D, but because of the mathematics of the deal is the 4D orbitals really are in the 3D. So for this guy, it would be 3D1 for scandium, and if it went to zinc, it would be 3D10. Okay, if we went over here. And even though it's in the fourth energy level, but the orbit itself is one energy level in. And that's why, but we don't have to worry about it until we hit number 21 and we go across. Okay. All right. Oh, got a question here. I got confused. Okay, well, we'll do some more examples of this. And what we're doing here is learning how to do the electron configuration for the elements. Okay, and that means where all these electrons that element has, where their electrons exist, what energy level they're in, and in what orbit they're in. Okay, and so we can do this one or two ways. We can fill it in, fill the electron configuration like this table shows us, and that's the order that they get filled in. The arrow going this way, 1s1, 2s, and then going from 2s to 2p to 3s. You can use that. Here's this sequence right here. Okay, now the 3Ds don't come into play until you hit number 21, element number 21. So you may not see the element. You may not need to do any Ds until you get to that particular element, if you're asked for it. So you may not see any Ds at all. And so you can use that sequence there to help you write the electron configuration, or you can utilize the periodic table with this information so that you can very quickly do the electron configuration of any element. For example, there's also a shorthand way. What I was writing was a longhand way. So let's do potassium. So potassium is in group 1, 2, 3, and 4. So we know we got 1s2, 2s2, 2p6. We went across there, we went across here. Okay. And then we went across the 3 energy level, so 3s2, and then the 3p level, fill that up, 3p6, and then we ended up over here with 4, and it's in the s, so we 4s1. So that would be the electron configuration for potassium. See how quickly we did that? I have to memorize that sequence. Okay, so this is the longhand way. You can do what's called the shorthand way. And the way you do that is you look at the element and you look for the noble gas preceding it. Here's potassium, the noble gas preceding it is argon. So we can write argon in brackets, okay? And then write 4s1, okay? Because argon, this is the electron configuration for argon. 1s2, 2s2, 2p6, 3s2, 3p6. So we can write it either shorthand way or longhand way. Which way we write it depends. If the question says don't do shorthand, then you have to do it longhand. If it doesn't say not to do shorthand, feel free to write it shorthand. Okay? And that would be for potassium. And guess what? Shorthand for calcium would be argon. Same thing, but 4s2 for calcium. Okay, and so forth. All right, so let me maybe stop it here. On number 27. So again, what we're doing here is learning about the electron configuration to give us insight into why metals want to lose electrons and nonmetals want to gain electrons, okay? For example, let me do a quick one here. Let's do fluorine real quick. Fluorine's right here, 1 and 2, so we got 1s2, 2s2, 2p, 1, 2, 3, 4, 5. See, this is fluorine. Okay, now fluorine is a nonmetal. And it has room for one more electron because that p orbits only has 5. So fluorine can readily pick up one more electron rather than lose 7. Think about it. Is it easier to lose 7 or just simply pick up 1? Well, here, picking up 1 makes a lot more logical sense because now it has the magical H. And by picking up 1 electron, fluorine now is a lot more stable because that last orbit, that last p orbit was missing 1 electron. Now that's full, it's got 8, it's reached that magical 8. And now you create fluoride, okay? Much more stable than fluorine by itself. And that is true for the nonmetals, like for carbon, there's 4. That means there's 4 valence electrons. It can either lose all 4 or gain all 4, gain 4. Depends on the condition. So it's on the hill. Okay, on the tip of the hill. So it's going to go one way or the other depending on the conditions, which means that everybody from 5 forward, they want to gain electrons because everybody in 5, group 5 will pick up 3 electrons, ending up with a -3 charge. Everybody in group 6 will pick up 2 electrons, ending up with a -2 charge. And everybody in group 1 will pick up 1 electron like fluorine to become fluoride. Okay. And the driving force is to get that 8. All right, let me stop it here. Slide 27. We'll continue.